Alright, hey everyone, thanks for being here. It's a lovely Saturday. Sorry I'm a little late. I forgot that they lock my building on weekends, so I have to sneak in through another building. But guess what? That's okay. We're gonna look at precise exceptions today. We're gonna wait on really doing the language streams until I can bring someone that speaks the language on, which should be in a couple weeks. But until then, I have research deadlines, specifically in 5 weeks. So we should probably do something research related. At least I'd think we should do something research related. I typically enjoy research. We all enjoy research a little bit. At least I like to think that we do. So we're going to look at precise exceptions, because I'm doing something exception related. It's not GPUs though, but to be honest, I don't know much about precise exceptions on CPUs. I know a little bit. I need to get better. Big shout out to Arhasius, our newest Prime subscriber. Thanks so much for joining. I think you're my second Prime subscriber ever. But guess what? Maybe the second Prime subscriber ever on this channel, but you'll always be number one in our hearts. Alright. Let's see if I can actually get this stuff working. It's so weird with the we'll play the title. Robbie Extra, how are you doing today, Robbie? You having a wonderful day? It's a great Saturday where I live. Is it a Saturday? Are you in the EU? Is it almost a Sunday where you live? Or are you having, more importantly, are you having a wonderful day? That's what's important. See, I added this extension, this chipated. I added this extension, you know, the whole Streamlabs thing for notification. I tried so hard to get it to work. And it should just work. Because it works for the donation goal. Well, actually I don't know if it works for the donation goal. I haven't tested the donation goal. Let's see. Add this one. This one's going to be notifications. But I usually have to do some weird screen capture thing. Yeah. See, if I add the Streamlabs thing, it's here, but then if I do a test, I get nothing. Except apparently it makes the other thing. Yeah, I'm sending tests right now, and it's not working. And it doesn't matter if I change it's not an issue of sources, or it's not an issue of which layer it's on. It's on the right layer. But we're going to look at precise exceptions today. Let me see if I can just do the screen capture for this thing. Get rid of this notifications box. Let's open up a new notifications box. Let's go here for a second. Let's launch it. If we launch it, and we go here, and we add a screen capture. No, that's not what I wanted to do. You know what? That's okay. We don't need that right now. This is a research stream. Let's get to it. Okay, let's pull up a browser. Precise exceptions on CPUs. Okay, let's go to owner's page. Here we go. It's Jim Smith's paper, right? Implementing. There we go. This is what I want. Jim Smith and Andrew Pleskin? Wisconsin-Madison guys. That's what's important. Okay. Is this the paper, though? I think this is the paper. Originally published 1985 in the Proceedings of Computer Architecture. Nice. Okay, let's download this. It's on edX. Why does it have an edX thing up here? Interesting. Okay. Let's open up. What's that thing I used to write on? External, external, whatever you want to call it. Smith Precise Exceptions. There we go. How are you all doing today? You guys must be having a wonderful day. It's a fine day to be alive, isn't it? Listen, the camera's ordered. Camera's coming in Monday. That'll be a lot of fun. Until then, you just have to listen to the nice, soft, soothing voice of Nick from Engineering Today. Okay. Let me go tell people I'm live. People might not know, and that'd be a shame. Okay. Got like 10 pins on my desk. Let's make sure I pick the right one. Okay. Let's see. So we have an implementation of precise interrupts on pipeline processors. Like we said, it's by Jim Smith and this Andrew Pleskin guy, both Wisconsin-Madison engineers. Older paper now. What is this going to be? 15, almost 35 years ago now, and still very relevant today. Modern, crack open your i7 processor. Well, it's going to be doing precise exceptions. It has to. So an interrupt is precise if the saved state corresponds with the sequential model of the program execution. So even though we're executing out of order, precise state exceptions means that we're able to save what the program looks like in some sequential fashion. So if this is our sequential program 5, and these are just some instructions out here. These, when they go into this thing called a reorder buffer, and in the reorder buffer, they get swizzled around because, we find some dependencies between them. And so this might be like 5, 2, 3, 1, 4 in there someplace else. But the thing is, they end up committing or retiring, depending on how you want to say it. Versuch, nice to see you here. We're going over precise exceptions today. I have, what's his name, Gershon? He's going to be joining us in about 2 weeks or so for the German teaching streams. So we can have a live German speaker, not a dead German speaker, a live German speaker. to correct me and keep me from developing bad habits. So like we said, we have some program, and then we have some reorder buffer. But when we finish our instructions, so we can call this a commit, we want them to still look like they committed in program order. So we still want it to look like it's sequential still. So we have to make sure that when they can finish in some particular order, but it's so they get, let's say we just put them in this thing, and this, we'll just leave a question mark there, and then this will eventually put everything in the right order and retire them in program order. Now, the key point here is what happens if we get some exception, if we get a divide by zero or a seg fault or something and the program crashes, right? So in the pipeline, so if we just kind of, here, let me make this a little more clear. So if I use a different color, and let's just use green for example. So if I isolate this here and I just look at the pipeline of what's currently being executed, so I'll consider this reorder buffer as part of the pipeline, commit in the program, they're part of the pipeline too, but if we consider the part of the pipeline where changes are actually being made, or we're actually doing some like computation and we're having some changed state, then, you know, if we crash here, we're not crashing in program order anymore. So our state's not going to look like, you know, whatever our commit history looks like. So maybe we finished instructions 1, 2, and 3 in commit, but in fact, we've done maybe, you know, instructions 5 or yeah, so we may have also done instructions 4 and 5 and 6 as well. But, you know, how do we know that? And because from the programmer's perspective, you know, everything's just happening sequentially. So we need a way to keep track of the state in here. So we need to, let's put our goals over here. So 1, we need to track state. 2, we need to replay. So after we handle some exception, we have to go back through and we have to re-execute after we handle the exception. Keep in mind, an exception may also be caused by a page fault. So here's a track state, replay exception. But not only do you need to track state, we also need to save state. So if something happens and we need to pull someone out of the processor or pull someone out during mid-execution, we have to keep track of where they are in their current execution. So we need to track state. In the process of tracking, we need to save state, and we also need some mechanism for replaying. So in a pipeline processor, precise interrupts are difficult to achieve because an instruction may be initiated before its predecessors have been completed. So instruction 5 may have been started before instruction 2 is done, instruction 3, instruction 1, but instruction 5 is already, you know, at the end of the pipeline. So this paper describes and evaluates solutions to the precise interrupt problem in pipeline processors. We don't consider precise interrupt problem in non-pipeline processors because that doesn't make sense. The precise interrupt problem is first described. Okay, then 5 solutions are discussed in detail. The first forces instructions to complete and modify the process state in architectural order. The other 4 allow instructions to complete in any order. So the first one we see we're going to get some pretty substantial overhead just because, you know, we're getting rid of this out of order execution. That's bad. We get a lot of performance from out of order execution. But additional hardware used to make precise state can be restored when an interrupt occurs. So This one, they're adding some extra hardware so that they can recover a precise state and restore it. Parallel pipeline structure. I think this was poorly translated. I don't know. I don't know who made this, but this should be structure. Okay, simulation results based on the Cray 1S scalar architecture are used to show that at best our first solution results in a performance degradation of about 16%. Robbie, this isn't even translating from another language. This is Jim Smith and Andrew Pleskin from Wisconsin-Madison. This is like text to speech, it seems like. This isn't like translating from another language. This is all in English originally. Okay, the remaining 4 solutions offer similar performance, so we get 60% performance degradation. But I mean, hey, 60% performance degradation is nothing. Every single person here updated their processor for the Spectre and Meltdown patch. We obviously don't care about just taking arbitrary hits to performance. This one's at least a good hit. This one at least does something. And 3 of them result as little as 3% performance loss, and that's pretty good. Several extensions, including virtual memory and linear pipeline structures, are briefly discussed. Okay. So we're going to find a way to handle exceptions while we're still doing this out-of-order execution. That's the key point here. The first one, very simple, but not very robust. We want to do something a little bit better. Okay. So most current computer architectures are based on a sequential model of program execution. So it seems like sequential, but it's actually out of order. So we go through one by one, finishing one before the next starts. In contrast, high performance implementation may be pipelined, where several instructions are in some phase of execution at the same time. The use of a sequential architecture has a pipelined and a pipelined clash at the time of an interrupt. Pipelined instructions may modify the process state in an order different than defined, or different from that defined by the sequential architectural model. So if we take 2 instructions, for example, so if we take add R3 from R1 and R2, and then we say subtract R4 from R2, R1, and I don't know. What else should we have in here? Oh, no, this should be fine. So what we assume happens is that if this is instruction 1, we'll execute it first and it'll complete. Then we assume this is instruction 2, it'll execute and complete. However, maybe there's some reason why. Maybe because of some dependency. Maybe, say, R3 is generated up here. And we don't want to immediately consume R3, so it might be better for us to do something that doesn't use R3 first. So we might do some reordering. And now we'll have instruction 2 above instruction 1. So we'll actually execute this subtraction R4, R2, R1, and then we'll do the addition. So we'll do add R3, R1, R2. Now, first glance, we go, it seems fine. I mean, there's no dependencies between these two things. Why should I care? Well, okay. Well, let's see what happens if we did this. And what if we crash right here? What if something happens and we crash and we want to recover from this? Well, instruction 1 may have started, it may have fetched the instruction already if we're talking about a pipeline processor, but Instruction 2 is already completed, so what color? We'll use this. R4 may have already completed, and R4 may have been updated. So now we have this state that is inconsistent with how instructions are ordered in the program. In the program, we expect we do an add and a subtraction. But if we do the subtraction, then we start the addition, and then maybe we crash someplace in here. Maybe there's something happens outside of our control. There's a crash. We get an exception. Well, we've changed the architectural state, but we're in this kind of gray zone because we're allowed to execute out of order, but if we try to say re-execute now, well, if we try to do things in program order, well, it's not technically correct because R4 shouldn't have been updated by the subtract yet. So that's this idea of precise state and why we care about this instruction reordering and why this presents an issue. So when interrupt occurs, the state of an interrupted process is typically saved by hardware and software or by a combination of the two. Okay, simple enough. The process state generally consists of the program counter, registers, and memory. And if the saved process state is consistent with the sequential architectural model, then the interrupt is precise. So this is not consistent with the sequential architectural model because in our program, in sequential order, R4 shouldn't be updated before this R3 is updated by this add. So we did something out of order. So the saved state should renew the following conditions. All instructions preceding the instruction indicated by the saved program counter have been executed and everything has been modified correctly. All the state, the memory, the registers, the program counter, they've all been modified in correctly by that point in the program counter. All instructions following the instruction indicated by the saved program counter are unexecuted and have not modified the process state. If the interrupt is caused by an exception condition raised by an instruction in the program, the saved program counter points to the interrupted instruction. The interrupted instruction may or may not have been executed depending on the definition of the architecture and the case of the interrupt. Whichever is the case, the interrupted instruction has either completed or has not started execution. So whoever caused the error, we want to point back to them, and we don't want them to be in some kind of middleman state. We want them to be, either completed and we have a set state where we know everything that's happened, or we want them to pretend they never did anything. But this, of course, determines on, like they said, the nature of the interrupt and the definition of their architecture. So let's just kind of run down these things again. So if we have our program and we have 1, 2, 3, 4 instructions here. Now let's say 3 is the bad guy. If 3 is the bad guy, even if we execute them in, say, the order of 2, 3, 1. Oh. Let's see. That's program order. Sorry. Let's say 3, 1, 2. Here we go. Or, yeah. So let's say that 3 is the bad guy. Actually, let's add one more in here. Let's add 4. So what we're trying to say here is, in number 1, all instructions preceding have been executed and have modified the process state correctly. So in this table of, so for number one just says in our commit, after 3 fails or something, our process state, if we go in this order, should look like this. We should only have 1 in here because 4 is ahead of us and it's after the failing instruction. 2 says all instructions following the instruction indicated by the program counter are unexecuted and have not modified the process state. So 4 we want to pretend never existed. So for 2 we'll just put a 4 and then we'll get rid of that. We'll put a 4 and then we'll give him a circle. I was going to do red. Okay, where's my red? There it is. We want to get rid of anything that's happened previously. And then 3, the interrupt caused by the precise condition raising, so it should be saved. Okay, so this just says, 3 just says our PC should point to whoever failed, which is 3 in this case. So 3 simple concepts. That's what we want to do here. And that's how we get precise state. So if the saved process state is inconsistent with a sequential architectural model, it does not satisfy, it's an imprecise. It's less useful to us. This paper describes ways of doing this. Okay, other more complex methods save portions of the process suite. Sweet. Is that supposed to say state? Other more complex methods save portions of... This is supposed to say state. Okay, so that's a typo. It's supposed to say state. This paper is killing me. So that the proper state may be restored by the hardware at the time the interrupt occurs. Okay. So for I/O and timer interrupts, a precise process state, send him an email. Send who an email? I don't know who wrote this. This isn't the writings of Jim Smith and Andrew Pleskin. This is before like online documents. This is from 1985. This was all on paper. So somebody had to manually copy this into this. This is from the companion CD-ROM for the IEEE CS Pressbook, Anatomy of a Microprocessor, by Shriver and Smith. I don't know who wrote this or who transcribed this from the original. Okay. So for I/O and timer interrupts, a precise state makes restarting possible. Okay. So for software debugging, it's desirable for the saved state to be precise. This information can be helpful in isolating the exact instruction. So keep in mind that if we do not have precise state, if an instruction fails, then we have a jumble of everybody's state together. So, it's hard for us to debug because who caused the exception? Well, I see 4 different instructions here that have all modified something. Which one was it? So, makes debugging a little harder. So for graceful recovery from arithmetic exceptions, so software routines may be able to take steps, rescale floating point numbers to allow the process to continue. Some in cases of modern floating point arithmetic systems might best be handled by software. Gradual underflow, proposed by IEEE Floating Point from 1981. So this just says, if we do something and maybe we get an answer of infinity in floating point, well, that might be for 32-bit floating point. So what if we use double precision floating point? And so 64 bits. Well, in that case, maybe the number's not infinity. Maybe it's just a really big number. So in virtual memory systems, precise interrupts allow a process to be correctly restarted after a page fault has been serviced. So it's beneficial for virtual memory.
Unimplemented opcodes can be simulated by system software as a transparent to the programmer if interrupts are precise. In this way, lower performance models of an architecture can maintain compatibility with higher performance models using extended instruction sets. So we can simulate opcodes now. So if something causes if say we want to run new software on old hardware, this says that if we have some instruction that's on the new hardware and it doesn't exist on the old hardware, and if we run that instruction and if we have precise state, well, it'll cause an exception. We can handle the exception in software, and then after handling the exception in software, we can simulate what that instruction is supposed to do with some predefined routine or something, and then we can just restart execution. And then virtual machines can be implemented if privileged instruction faults virtual machines can be implemented if privileged instruction faults cause precise interrupts. Host software can simulate these instructions and return to the guest OS in a transparent way. Okay. So we should talk about interrupts first. It's usually a good idea. We're talking about handling interrupts, so we should probably talk about interrupts too. Okay. Let's just... Okay. So let's see. Okay, so we have program interrupts, so often called traps, result from exception conditions detected during fetching and execution. So these can be due to software errors, things like illegal opcodes, numerical errors such as overflow, or they may be part of normal execution, like page faults. So program interrupts will be things like divide by 0 will be a program interrupt, or if we get some result that's infinity or something, probably want to catch that. Those would be numerical errors. And then illegal opcodes, that. And then, let's see, and then page faults, of course. So if the page isn't in memory and we need to fetch it from disk or something, well, that causes an interrupt. So what's an external interrupt? So these are generally I/O devices. So I/O, often called I/O interrupts, and then timer interrupts, are not caused by specific instructions but caused by outside sources. So like the watchdog timer, things like that. For a specific architecture, all interrupts have to be defined to be precise or only a proper subset. Virtually every architecture, however, has some types of interrupts that must be precise. There are a number of conditions under which precise interrupts are either necessary or desirable. Okay, we went over that. The historical survey we can skip, I don't care. Preliminaries, okay. Model architecture. We could talk about the Cray, but I mean, why are we talking about a computer that's 4 decades old? For describing the various techniques, a model architecture is chosen so that basic methods are not obscured by details and unnecessary complications brought by specific architectures. So we want to make this general, a general kind of design. So we choose a register-register architecture where all memory accesses are through registers. And all functional operations involve registers. So we're not doing, it's not like x86 where you can do some addition with a register and an immediate and a value in memory. We're saying we can only have registers as the arguments. So in this respect, it bears some similarity to CDC and Cray, but has only one set of registers. The load instruction are of the form RI equals RJ plus some offset or displacement. So basically, they're saying that some register will hold the address we're trying to load from memory. Okay, yep, this is just describing that kind of stuff. This is supposed to say state, but it says suite. The only process state in the model architecture consists of the program counter, general purpose registers, and main memory. The architecture is simple, has a minimal amount of process state, can be easily pipelined, and we can have parallel functional units like CDC and Cray. Hence, implementing precise interrupts for the model architecture presents a realistic problem, because at the time these were the leading architectures. So initially we assume no operand cache. Similarly, condition codes are not used. They add other problems beyond precise interrupts. Then, I guess there's supposed to be a period here. Then a pipelined implementation. I feel like I got a first draft of something. Then pipelined implementation is used. Extensions for the operand cache are section 8. Okay. Anything else here? No, we can just skip to example 1. To demonstrate how the imprecise process state may occur in our model architecture, consider the following section of code, which sums the elements of arrays A and B into array C. So we're doing the vector operations. First draft from 1980. Maybe. It's likely what this is or something. Although, if it was a first draft from 1980, this would likely have to be a scanned version. Okay. Consider the instructions in statements 6 and 7. So where's statements 6 and 7? Oh, here we go. These are out of order. Okay, so what do they have here? They have a floating point add, where they're adding R1 and R3, storing in R4. And then next, they're incrementing some loop, so they're adding R0 plus R5, which, okay. Although the integer add, which increases the loop count, will be issued after the floating point add, it will complete before the floating point add. And so this is because, so if we look at an example of this, so we say, we'll consider a 5-stage pipeline, so it'll be fetch, decode, execute, memory, write back. So if we consider, yeah, R5 is undefined. Yeah, it's undefined here. I mean, we'll just pretend that, R5 up here is 1. There you go. R5 is defined now, so at index -1. Okay. So in fetch, decode, execute, memory, write back, what this is saying is that if we look at instruction 6, we will be, say, doing fetch, decode, execute, memory, write back, and then let's even expand this out. Say execute takes 6 cycles, so fetch, decode, execute, memory, write back, and then in the next clock tick we fetch instruction 7, so this will be 6 and this will be 7. We'll do fetch, decode, execute takes 2, memory, write back. So even though this executed first or issued first, this guy finished 4 clock cycles ahead, right? So that's what they're saying. The integer add will therefore change the process state before an overthrow condition has been detected. So in such an event, an overflow, there is an imprecise interrupt, and this is because if somewhere here we get a overflow, well, we're already done with our next instruction here. So we've already updated, what is it in this case? We've updated R3 or R0 already. Yeah. So in this case, R0 has been updated out of order. And in fact, GPUs, they really fall under this model because instructions are issued in order, but they finish out of order. Okay. So, at least NVIDIA GPUs. I don't know anything about AMD GPUs, honestly. I know that they use 64 thread, what are they called in NVIDIA or in AMD's architecture? They don't call them warps. They call them something else. They're basically, if you're used to NVIDIA terminology, they use 64 threads in a warp instead of 32. So the integer add will therefore change the process state before it's been detected. In this event, there's an imprecise interrupt. Okay. So there's a pipeline implementation of our model architecture. Not shown is the result shift register used to control the result bus. So let's see what happens here. We have our register file, we have memory access, we have instruction fetch and decode. So we have these parallel functional units where when we issue an instruction, say if we're, in this case they're talking about doing some vector A plus some vector B and then storing that in C, which is, of course, implicitly it's going to be another vector of the same size. So that's our model architecture, at least the pre interrupt handling version, or precise interrupt handling version. So interrupts prior to instruction issue. So that was after instruction issue. Now let's look at interrupts prior to. Okay, so they talk about this. So they talk about figure 1. Further, let's see, in the pipeline, instructions stay in sequence until the time they are issued. Furthermore, the process state is not modified by an instruction before it issues. This makes precise interrupts a simple manner when an exception condition can be detected prior to issue. So you can consider all of these guys, these functional units, they're all running a race. So, this guy might, he goes out of here super quick. But this guy up here, he might just be chugging along, and eventually get out. So they all still come in order, but we have this idea of finishing out of order. So if we want precise state in this model, well, we need to detect it here. Because here, or rather, we need to detect it here. Because at issue, everything's still in order. It's still sequential. So what happens? So when such an interrupt condition is detected, we just stop issuing, and we wait while all previously issued instructions complete, and the process is in a precise state with the program counter value corresponding to the instruction being held by the issue register. So if the guy in here is what's causing the problem, well, we'll just save whatever the program counter value is for that instruction. Because exception conditions detected prior to instruction can be handled easily as described above, we will not consider them any further. So we want to discuss the interesting problems. If we can just detect it ahead of time, well, then just detect it ahead of time. But it's probably more useful for us to. It's probably a lot more useful for us to tackle the difficult problems, and academically, it's probably better work too. So in order instruction completion. With this method, instructions modify the process state only when all previously issued instructions are known to be free of exception conditions. This section describes a strategy that is most easily implemented when the pipeline delays in the parallel functional units are fixed. So this says that this case no longer happens and that everybody's going to have the same fixed length now. So now, if this guy takes, 3 ticks, this guy will take 3 ticks. And everyone's going to finish on time in a predictable fashion. It's not efficient, but it works. Sometimes we want to test a naive implementation first. Thus, an extra period here. The result bus can be reserved at the time of issue. Okay. So first we consider the method commonly used to control the pipeline organization in Figure 1. Excuse me. Yawning. I need coffee. Let's see. However, the precise interrupt method described in this paper are integrated onto the basic control strategy. To control the result bus, a result shift register, seen in Figure 2, is used. So here the stages are labeled 1 through n, where n is the length of the longest functional unit pipeline. So this is Figure 2. So what do we have? So we're moving up. Functional unit, so 2. So here we're keeping track of the stages, we're keeping track of the destination register, we're keeping track of the functional unit source, so where we're getting our result from. Is it coming from some integer unit? Is it coming from some floating point unit? Where's it coming from? Where's it going? If the result's valid yet, meaning if it's finished, and then what's the PC value? An instruction takes I clock periods, reserves stage I of the result shift register at the time it issues. So basically this is saying if it takes 2, so in this case an integer add. So we have an integer add right here, right? And it says it takes 2 clock cycles. So then we would reserve slot 2 in this result shift register. I think that's what it's saying. An instruction that takes I clock periods reserves stage I. Okay. If the stage already contains a valid control information, the issue is held until the next clock period. So we just we hold everything at issue until we have, in our result shift register, we have some space. An issue instruction places control information at the result shift register. This control information identifies the functional unit that will be supplying the result. Let's see. Let's read this again. I skimmed over this too quickly. An issuing instruction places control information in the result shift register. This control information identifies the functional unit supplying the result and the destination register of the result. Okay. This control information is also marked valid with the validity bit. Each clock period, the control information is shifted down 1 stage towards stage 1. When it reaches stage 1, it is used during the next clock cycle to control the result bus so that the functional unit result is placed in the correct result register. So still disregarding precise interrupts, it is possible for a short instruction to be placed in the result pipeline in stage I when previously issued instructions are in stage J, where J is greater than I. So this says if we get a short instruction, so if we get an instruction that's 2 clock cycles, let's say 2C, or better yet, 2 tau. If we have, other instructions in this table that are, say, 6 tau, it says that we can take this 2 tau 1 and we can insert it, and if we're moving this direction, that, you know, we can execute this short instruction first. So in this case, this would be I, and then this would be J. If the instruction at stage J eventually encounters an exception condition, an interrupt will be imprecise because the instruction placed in stage I will complete and modify the process state even though the sequential architectural model says I does not begin until J completes. So this is some out of order execution stuff. Implush. Hello, my friend. Thanks for joining us today. Are you having a wonderful Saturday? I'm having a wonderful Saturday here at the stream. It's your good old pal Nick from engineering today. Okay, so example 2. So if one considers a section of code presented in example 1 and an initially empty result shift register, all the entries invalid, so there's nothing in them, so we consider them invalid at that point. The floating point add would be placed at stage 6, and the integer add would be placed at stage 2. So the result shift register entries shown in figure 2 reflect the state of that case. So in this case, that integer add that we were talking about, because it takes 2 clock cycles, gets put in the second slot. And then this floating point add that takes 5 cycles gets put in stage 5. And then we mark them both as valid because we put an instruction here. What did you study in your undergrad? I did electrical engineering. I started out doing mechanical engineering. Then after I did mechanical engineering, I decided, wow, I really don't like mechanical engineering. And then I did electrical engineering, and I did control systems. And then after I did control systems for a while, I took a class in digital design, and then I realized I liked computer engineering. And then I became a computer architect. That's my quick journey through education. I bounced around a little bit, but hey, sometimes we need to do that to get where we're going. So notice that the floating point add entry in stage 5, since 1 clock period has passed since its issue. Okay. So it gets issued and then 1 cycle later. So that's why it's not 6 here. So it says 6 here, but it's already been issued. And so that'll be the first cycle. That's awesome. I'm doing CS and applied math. I wish I could switch to electrical engineering or computer engineering. Hey, you don't have to worry about switching to electrical engineering or computer engineering. There's nothing wrong with getting a CS degree. In fact, listen, I don't know what you want to do with your career, but there's so much overlap between computer engineering and computer science. You know, I think even at Wisconsin-Madison, computer science and computer engineering are like the same degree, I think. I'm not at Wisconsin-Madison, but I think that's the case. It all depends on what you want to do. And at the end of the day, an undergrad degree doesn't really... It really just gives you some knowledge on some foundation, so I wouldn't worry about it too much. I switched mainly because it was a completely orthogonal field, so I really didn't like mechanical engineering, so I switched to computer engineering. And then the same was the case for... it wasn't really the same case for control systems. I liked control systems, but part of it was a practicality because I looked at control systems and I saw that it's a very mature field and there's not a lot of jobs in it. So I wouldn't be doing something very interesting, most likely. And then I looked at computer engineering and I thought it was all fun. It was pretty fun, and there was a lot of room for growth. And I personally like the idea of a fast-moving field. As described above, this situation leads to instructions finishing out of the original program order. Sure, and that's because we're doing this insertion thing, right? So even though this floating point add comes first, when it gets into this result shift register, we're actually putting the floating point behind this integer add. Okay, so we want to talk about registers now. I like registers. Registers are what makes precise interrupts on GPUs so hard because there's so many. Well, I'd love to get a job somewhere closer to hardware. I can't switch now because I'm in my junior year in CS and applied math. Oh well, maybe in another life. Listen, it's never too late if you want a job in hardware. It depends what you say by you want a job in hardware. The simple case is, I mean, with the layers of abstraction we have, it depends what you mean by hardware. Now, if you mean something like writing Verilog or VHDL and designing or writing RTL and being on the devices side of things, well, yeah, you probably have a pretty steep learning curve. But if you want to do something like computer architecture, I'd imagine that someone in the CS department would be fully capable of doing that. In fact, there are, in most schools that I know, a lot of people that are in the computer engineering department that do computer architecture research are computer science PhDs. So, yeah, I wouldn't count yourself out of a more hardware type position. Okay, to implement precise interrupts with respect to registers, the above pipeline control structure, the control should reserve stages I greater than J, or I less than J, as well as stage J. That is, the stages I less than J should not be previously reserved by other instructions that are reserved. So this says that when this guy comes in, it says that everything kind of going down this path. Oops, let's get the pen. It says that everything here, we should reserve it. That way, no one else can take it while I'm working on this floating point add. Okay. So what else do we have to do? Tell me, Jim Smith, what else do we have to do? This guarantees that instructions modify registers and finish in order. Okay. That's good. There's logic on the result bus that checks for exception conditions in instructions as they complete. If an instruction contains a non-masked exception condition, then the control logic cancels all subsequent instructions coming on the result bus so they do not modify the process state. So it says that in this case, the ordering would be, first, we do this reservation so that this integer add can never be issued until we're done. Then, if, say, this floating point causes an exception, well, we want to make sure that no one else modifies the state after this floating point, so we have to squash them. So, cancels all subsequent instructions. That's what we mean by squashing. So let's look at example 3 now. So we're getting a little bit better. We're making it so that we at least know that the registers will be in the correct spot. For a sample section of code, given in example 1, assuming our result shift register is initially empty, such a policy would have the floating point add instruction reserve stage 1 through 6 in the result shift register. When on the next cycle the integer add is in the issue register, it would normally issue and reserve stage. However, this is now prohibited, so that's what we're kind of saying. So we're saying right now that, we can, that's exactly what we just went over, the fact that we can now just say, hey, stop, don't issue. It just seems like engineers work on more interesting projects even in undergrad level. I don't want to end up being a web developer, might as well go back to school once I have some money, save up and do EECE. Kind of lost respect for CS, and I don't know why. Well, I think the big thing is it doesn't take any computer science knowledge to become a web developer, right? So computer science and programming they're not the same thing. Programming is not a subset of computer science. So you don't have to be, if you're a programmer, you're not a computer scientist. Yeah, I know, but that's the most common job, Maybe. I mean, it depends what, it all depends what you want to do. So my suggestion is the first thing you should do is to figure out what you want to do, because the problem with something like web development is that not only are you maybe competing with other people that are computer scientists, people with CS degrees, you're also going to be competing with every Tom, Bill, and Lucy that went to a programming boot camp. Because in order to do web development, I'm pretty sure that doesn't require any theoretical computer science knowledge. You know, generally the people that are doing web development aren't, digging into what's the algorithmic complexity of, this HTML page, right? You just need to go to boot camp for 3 months to learn X framework. Yeah, so it just depends what job you want. If you and boom, well, I mean, the thing is that market's super saturated, right? Like those types of jobs are the employers can be very selective because you can just go to a boot camp and learn it. I shouldn't say just go to the boot camp. It does take some effort, but it's not exactly a super technical skill, and it's something that you can have sweatshops for code in India do the same thing. And not to mention it's an automatable skill. That's what, they don't do, the best job, but things like, what is it? Is it Squarespace and, what's the other one that's popular? Things where you automatically build websites. It makes it WordPress. That's the other one. Yeah, they don't do like the greatest things. However, for most people, it's also extremely boring. You can't go to a 3-month boot camp and become an engineer. No, not really. You can even do shops. Yeah, I don't consider software engineering real engineering. Well, that's not true at all. So, I mean, software engineering is a much wider scope, though, than... software engineering is a much wider scope than something like just web development. So I wouldn't consider software engineering not real engineering, though. I'm not a software engineer, but still. Listen, Implush, what do you want to do? You said you're more interested in EECS, but what do you want to do in EECS? What do you want to do in EECS that you can't do with a CS degree? Because most jobs in a lot of computer engineering type places, or most computer engineering type jobs, if you look at the job descriptions, they say looking for computer engineer, computer science, or related field. So I'm not sure where, unless you're like trying to do something like, I don't know, signal processing or something. Yeah, I mean, let's just pull up some stuff, right? We went job searching for one of my friends the other day. Let's just look up computer architecture jobs. Let's look up undergrad. You did signal processing in your CS undergrad? Just one course, though. Well, it depends what you mean by signal processing. So most people don't do the theoretical. So you do 5G network. So most people don't do the like theoretical signal processing because that's typically an EE or what is it? What is the field it normally is? It's at my university. It's called CNSIP, which is Communication Networks and Communication Networks Information Signal Processing. Computer architecture jobs. Let's only look at good jobs. So, well, that's a firmware engineer, so I guarantee that it has MS, electrical engineering, computer engineering, and computer science. Design verification engineer. This isn't very interesting. BSEE, a computer engineering or related field of study. So you would be in the related field of study. Discrete Fourier transform, signal noise ratio, some filters. Okay. Sure. I mean, that sounds like an interesting little processing course. Let's see. Design engineer, new college graduate. BACE, computer engineer or related field of study. So related field of study again. FPGA, hardware engineer. BS, MS in computer science, computer engineering, electrical engineering, or physics. Firmware engineer is, of course, going to have that. This one just says electrical computer engineering. But I mean, they're not going to turn down a computer scientist. 3D firmware engineer. Interesting. Yeah, I mean that's like it's a higher up job. Software development engineer. This of course will have CS in here. Computer science or related field. So I mean, I just looked up computer architecture jobs and look at all the things we found. So, it's not exactly like you're you're not qualified for any of these other jobs. In fact, graduating from undergrad, you're not qualified for any job, really. 40-year experience at 20 years old. Yeah, exactly. Okay. I don't know why I didn't look for jobs other than web dev. Yeah, listen. I mean, just think of it this way. Nobody graduating is qualified for anything because Dell doesn't care that you know how to solve some problems that was in a book. Those problems were solved 80 years ago. Like if you look in algorithms book, or if you look at a computer architecture is a great example. Let's talk about computer architecture for a second, since I'm doing my PhD in computer architecture. So let's talk about something like out of order execution. Out of order execution is something that isn't even. I'm pretty sure out of order execution isn't even taught at the undergraduate level. It may be mentioned, but it's not even taught. Out of order execution was invented in like the 60s. So if you're trying to get a job at Intel or something, just realize that no undergrad is qualified for that job at Intel. So no one's really qualified based upon their undergraduate degree. Their undergraduate degree gives them the context to learn whatever they need to learn at their job. But I wouldn't say your undergraduate degree really qualifies you for a job. Boot camps qualify you for a job more than an undergrad degree because boot camps are specifically on the practical implementation. They should do more internships. Some schools have mandatory internships for students. At least that's what my somebody I did research with in undergrad, they had to do that. SNR is signal to noise ratio and DFT is discrete Fourier transform. It's signal stuff. I'm taking the answer away from you, Robbie or Roby. Okay, let's get back to the research. Okay. So what do we have? What do we have here? So a generalization of this method, so this is this idea of reserving all the spaces and then squashing later instructions if we hit an exception. is to determine, if possible, that an instruction is free of exception condition prior to the time it is complete. Only result shift registers that will finish before exceptions are detected need to be reserved. Let's see. Nyquist plots. Yikes. People even do Nyquist plots? I thought everyone just used Bodhi plots, right? Nyquist plots were actually invented as the same time as Bodhi plots. They were just developed like independently. I think Nyquist plots were like invented in like Russia, and then Bodhi plots were invented like behind the Iron Curtain, and then Bodhi plots were invented in like the West, and so they do the same thing, but they're completely different. Or not completely different, but they're different. Okay. So how do we generalize this method? So determine that the instruction is free of exception before it's complete. Only result shift register stages that will finish before exceptions are detected need to be reserved. This sentence doesn't make sense. I'm going to skip this. I'm going to skip that because they don't know how to write. They don't know how to transcribe correctly. Store instructions modify. So now we need to talk about how do we make precise exceptions deal with main memory correctly. So store instructions modify the portions of process state that reside in main memory to implement precise interrupts. With respect to memory, one solution is to force store instructions to wait for the result shift register to be empty before issuing. Alternatively, stores can issue and be held in the load store pipeline until all preceding instructions are known to be exception free. Then the store can be released to memory. So load store pipeline, we can throw out and issue a bunch of loads and stores before. It takes a lot longer to actually process the loads and stores, but generally we only care about loads, right? Though, because if we talk about stores we're just throwing something to memory, and we're not going to. The idea is we're probably not going to be using it recently. Okay. To implement the second alternative, recall that memory can be treated as a special functional unit. So, okay, well, if we just treat it like a special functional unit, we might be able to do a little better. Thus, as with any other instruction, the store can make an entry in the result shift register. This entry is defined as a dummy store. The dummy store does not cause the result to be placed in registers, but it's used for controlling the memory pipeline. The dummy store is placed in the result shift register, so that it will not reach stage 1 until the store is known to be exception free. When the dummy store reaches stage 1, all the previous instructions have completed without exceptions, and a signal has been sent to the load store unit. So do they have an example of this here? Reorder buffer, let's just reorder buffer. So basically the main idea is that if we put some dummy instruction in here, that's a memory instruction now, so let's get rid of this reservation stuff. Now the idea is, okay, well, let's get rid of this integer again. Now let's pretend this floating point is instead a load. Now in this case, we're just going to put it in here. We're going to let it kind of crunch. We're going to let it go to memory, get any data we want, and then everything ahead of us, it will complete. It'll finish without exception, and then it'll only get to 1 if we know it has no exceptions. Okay. What kind of projects do you recommend I do, hopefully to get a job somewhere involving hardware? Uh, I don't know. It depends on what kind of job you want in hardware. Hardware is a pretty big field. There's a lot of different kinds of hardware. There's embedded systems. There is system software. There is Beryllium, my dude. How are we doing today, Beryllium? Let's see. There's architecture. There's all the way down to designing the actual hardware. There's a ton of jobs. I'd rather prefer math, but programming is okay, I guess. I don't write a ton of code. I'm much more interested in architecture than writing code, which is why I'm an architect. Let's see. Learn how to program microcontroller. That's a great idea, Robbie. Microcontroller programming is, if you want to get into hardware, that's the perfect way to start blending CS and hardware, because when you're generally programming a microcontroller, you have to really read whatever the docs are for that microcontroller. Order $1,000 FPGA. That's the next step. I mean, only if you want to write frickin' RTL. You don't need an FPGA for anything else. The FPGA requires you to write RTL. And I'll let you in on a secret. There's not a ton of people that write RTL. That's a different subset. You can't design architecture your own? What? I don't know what you mean. What do you mean you can't design architecture on? So there's not a lot of stuff you can do to get a job? I mean, the jobs don't ask you to have a portfolio, though, of having built an architecture. What jobs will ask you is questions dealing with architectures. They don't care if you can, hey, look, I built my own nifty architecture that's awful. You know, what they care about is, hey, do you know anything about x86? Do you know anything about ARM? Do you know anything about RISC or MIPS or something? They'll ask you questions about those architectures. So, on the architecture side of things, you really should just read an architecture book. Just like the one that I go over my channel every Monday at 7 p.m. Eastern Standard Time. So, I mean, if you want to do computer architecture, if you want to, I don't know what you want to do. So here's the first thing. Implush, here's my first guide for you. First, you got to survey the field. You got to figure out what jobs you actually want. Because you say hardware, but hardware, that's like saying, I want to do something with software. Okay. Well, does software mean... Let's see. Does software mean, do I want to do web development? Do I want to do embedded systems? Do I want to do operating system stuff? Do I want to write drivers, firmware? Well, it's a wide field. So the same things with hardware. Hardware, it's like, okay, well, do I want to do embedded system stuff? Do I want to do operating system stuff? Do I want to do drivers? Do I want to do RTL? Do I want to do architecture? You know, there's a lot of things. So my first thought would be, hey, look around, see what you have, see what jobs pique your interest, maybe read some blog posts about, you know, what these types of jobs do, and if it sounds interesting, you know, then you'll kind of figure out what you want. I mean, it's kind of like what I did. I went out not knowing much about any kind of engineering, so I thought mechanical engineering sounds cool. So I did some mechanical engineering. I did about a year and a half of mechanical engineering. Then I decided, wow, I learned statics, I learned dynamics. I was going to take a materials class, and I was like, I really don't like this. But I took a circuits class, and I thought, I do like this. And so, that's pretty good. So what I did was I became an electrical engineer. And then I took some stuff, and I took some stuff in control systems and signal processing, and semiconductor device fundamentals. And then I took some stuff in intelligent control as well. And then I thought to myself, well, I took a class. These are all pretty good. I like them. Job market's not great for them. And then I thought, I really like that digital design class I took. So I took a class that was in computer architecture, and I took a class that was in digital system design, and a class that was on computer arithmetic, and I was like, all right, I'm a computer engineer. But, I only got there because I figured out what those people did. And the only reason I'm doing a PhD now in computer architecture is because, I took an undergrad class in computer architecture, or I learned about computer architecture, and I thought, this is pretty neat. This is something that I'd like to do. Job market isn't there for intelligent control. You don't need to know a ton of control theory to do intelligent control. You need to know how to use TensorFlow. Intelligent control basically takes the control theory out of control. Intelligent control is generally applied machine learning. So you typically want someone that knows how to apply machine learning more than you want someone that's a control theory expert. Because what is machine learning really? Like when you're doing training, you give it inputs and then you give it the correct outputs and then you give it arbitrary inputs and you see if it's close, right? Well, how much control theory goes into that? I mean, anyone can see what I want it to do and then what the output should be. You learn 20 years to model systems and a GPU does it in 20 minutes. Hey, sometimes it takes a couple days to do training. But someone who can apply ML and control in an abstract way is useful. Oh, sure. I'm not saying there's not a little niche position out there, but I'm saying it's a niche position. It's not the controls field isn't that big. We've solved a lot of the problems. I would say that in control theory, places like SpaceX need control theory people, right? They absolutely need control theory. And places that do big mechanical projects need control theory. But it's not a super wide open field, right? It's not like computer engineering where there's not enough people. Same thing with computer science. There may be plenty of people that know how to make web pages and do web development. However, there's not people at the next level, right? The level that... So people make this misunderstanding of like, we're not graduating enough people for computer science. And the problem more is we're not gradually... the people we're graduating aren't at the level that we have the biggest need, right? Abstract control of an arbitrary system of which you have no knowledge of. That's one of those big problems, right? And people want to use machine learning to solve it, but that's not a super big field. That's the only point I'm making. I'm not saying that the field doesn't exist. I'm saying that it's just not very big. It's not like machine learning or computer architecture or something like that. Okay. The Space Force. Listen, don't get me started on the Space Force. You know what the Space Force is? It's nothing special. The Space Force is just going to be the space part of the Air Force get branched off into a different branch, which it should have probably happened years ago. So all the satellites and surveillance stuff is probably just going to be moved to the Space Force, right? Okay. So we talked a little bit about memory. We talked about how we can save memory. Oops. Highlighter's not on. Here we go. Now, the third thing we need to save, so we said we need to save the register file, and we need to save the state of memory, but last thing we need to save program counter. So to implement precise interrupts with respect to the program counter, the result shift register is widened to include a field for the program counter for each instruction. Okay. So basically this just says that, we've made it so that instructions will only be in order in this result shift register. And we'll add another column in order to say which program counter called the exception, right? So nothing terribly fancy. We just add another, couple of bits tagged on at the end of this table. Okay, so now we get to the reorder buffer. ROB. So the disadvantage to the above method is that fast instructions may sometimes get held up at the issue register even though they have no dependencies and would otherwise issue. In addition, they block the issue register, while slower instructions behind them could conceivably issue. This leads to more complex but more general solution. Instructions are allowed to finish out of order, but a special buffer called the reorder buffer is used to reorder them and modify before they modify the process state. So we'll have all these instructions, but before they change anything, we can swizzle them around in some way that we want in this structure right here. So what's the basic method? So how are we going to accomplish this? So the overall organization shown in 3A, which is here. So we have this result shift register, which provides some control to the reorder buffer. The result bus, it's getting its results from elsewhere. And then this reorder buffer is swizzling around things as needed before it actually commits anything to something like the register file. So the reorder buffer in figure 3B is a circular buffer with head and tail pointers. Entries between the head and tail are considered valid. At instruction issue time, the next available reorder buffer entry pointed to by the tail pointer is given the issuing instruction. The tail pointer value is used as a tag to identify the entry in the buffer reserved for the instruction. The tag is placed at the result shift register along with the other control information. The tail pointer is then incremented, modulo the buffer size, of course. The result shift register differs from one used earlier because there's a field containing a reorder tag instead of the field specifying the destination register. Okay. So here we have the reorder buffer now, where we have entry numbers. Everything between the head and tail is considered valid. So everything outside of that is invalid. We have destination register, where we're going to commit these changes of state, what are the results is, if it caused an exception or not, if it's valid or not, and then the PC value. Now we have the tag, which says, okay, now where do I belong in the reorder buffer? We have the same valid bit now. And we still have what stage we're in the result shift register. And then also whatever functional unit we're using. Okay. So when an instruction completes, both results and exception conditions are sent to the reorder buffer. The tag from the result shift register is used to guide them to the correct reorder buffer entry. When the entry at the head of the reorder buffer contains valid results, so i.e. when it's finished, then its exceptions are checked. If there are none, the results are written into the registers. If an exception is detected, issue is stopped in preparation for the interrupt, and all further writes to the register file are inhibited. So we basically just stop our committing or retirement of these instructions out of the reorder buffer. Example 4. The entries in the reorder buffer and result shift register, shown by figure 3b, reflect their state after the integer add in example 2. Okay, 3b. So after the integer add in example 2, we now have our add in stage 2, our floating point in stage 5, both valid. Now these have to have a tag within the reorder buffer now. So 5 and 4 respectively. And if we remember from back up here, at instruction issue time, the next available reorder buffer entry pointed to by the tail pointer is given to the issuing instruction. So here is whatever's next. So 4, 5. So 4 came first, then 5. So whatever the most recent instruction is going to be closer to the tail. So here we get added to the reorder buffer, so this guy's at the head. So its destination register is 4, because if we look back at the code, yeah, it's this guy, R4. The other guys should be R0. Yep, which certainly, this is R0. They're not valid yet because the results haven't come in, and then we saved whatever the PC value is now. Okay. The integer add will complete execution before the floating point add, and its results will be placed in entry 5 of the reorder buffer. These results will not be written until R0, written into R0 until the floating point result found in entry 4 has been placed by R4. So now we have a way of reordering these out of order instructions in a way that makes sense, because now it looks like even though they executed out of order, we commit them in order. A very key point. Okay. Does that make sense to everyone? Everyone having a wonderful time? How's everyone doing still? Everyone excited to learn about something that happened in 1985? Oh, good. Robbie, I'm glad you're having a nice time. This happened in Listen, this is how you have to just kind of give the utmost respect to these early computer architects. They did so much stuff for this field. So preciseness with respect to memory is maintained in a manner similar to that in the in-order completion scheme in 3.2. It's like history class. It is like history class, except it's like history class, and it's like a computer architecture class, because this paper it's history. But the thing is, here's where it gets fun. This is what's still used today. We still do precise exceptions in a very similar way. We've optimized it, but the core idea is the same. We still use reorder buffers. So the simplest method holds stores in the issue register until all previous instructions are known to be free of exceptions. In the more complex method, a store signal is sent to the memory pipeline as a dummy store is removed from the reorder buffer. So basically what happens is, in the more complex way, we tell the memory pipeline, hey, we want to store something, and then in our normal execution pipeline, in the reorder buffer, we put a dummy there that we'll just kind of hold on that dummy. AI was invented in the 50s, revamped in 2008. Yeah, it was invented in the 50s. It was big again. Most of the modern things, I think, were invented in the 80s. And then finally it came into existence in early 2000s. Robbie, if you haven't seen the If you haven't seen here, I'm going to link it in chat. It's a very interesting thing that you guys should watch if you get the time. It's about the AI revolution, and it's from Bill Daly. He's the chief scientist for NVIDIA, and he's talking about the AI revolution. It was from ISCA 2017. Bill Daly. No. Is it this? Oh, yeah, it's this. Okay. Here you go. Watch this sometime. It's a great thing. You don't need to watch the entire thing because it's like a keynote. But if you would just watch like the beginning portion of it, it's very interesting because he goes over the history of neural networks, or the history of machine learning as it relates to hardware. Okay. So now that we've talked about that, we can just put a dummy instruction there, and we can just kind of wait on the dummy instruction. No, how do we handle things with like the program counter? 720 views. Now, listen, it's always so sad, some of these things, because they're the most amazing videos ever. Like, there's a video that I linked to another friend of mine in a different chat, and it was from the most recent ISCA, and it's an amazing lecture, but it's the same thing. Insert Fortnite in the title, 20K minimum. Fortnite architecture, you've got to see it to believe it. Gone viral. What's another keyword? Almost died. Gone bankrupt. There you go. Okay, so how do we save the program counter? So we need to maintain preciseness with respect to the program counter. The program counter can be sent to a reserved space in the reorder buffer at issue time. So we just save the program counter as well. We just give it another slot in the reorder buffer. While the program counter could be sent to the result shift register, it is expected that the result shift register will contain more stages than the reorder buffer and thus require more hardware. The length of the result shift register must be as long as the longest pipeline stage, as will this is supposed to say B, but it says he, as will be seen in section 7. The number of entries in the reorder buffer can be quite small. When an instruction arrives at the head of the reorder buffer with an exception condition, the program counter found in the reorder buffer entry becomes part of the saved process state. Okay, or precise state. Okay, so we can have these things are different sizes. Remember, it's not all one homogeneous size. Bypass path. Okay. So while an improvement over the method described in section 3, the reorder buffer still suffers a performance penalty. A computed result that is generated out of order is held in the reorder buffer until the previous instructions, finishing later, have updated register file. Okay. An instruction dependent on the result being held in the reorder buffer cannot issue until the result has been written into the register file. So this just says that, okay, well, right now, if we go back to the code, right now we have this R0 right here, right? And we can finish this add really, really quickly. Now, what if there was some other instruction that wanted to use this value? Well, it can't. It can't use this value, even though it's already been computed, because it hasn't been committed yet to the register file, because it's still waiting out in the reorder buffer until the floating point comes back. We check to see if there's a value, and then we check to see if there's an exception. We're still waiting on that. Okay, but the reorder buffer may be it may be modified to minimize some of the hardware drawbacks of finishing strictly in order. For results to be early, bypass paths must be provided for entries in the reorder buffer to the register file output latches. These paths allow data being held in the reorder buffer to be used in place of register data. So in this case, we're bypassing the register file with data that we've computed in the reorder buffer, but we haven't committed yet. as long as it stays in the reorder buffer, we can still guarantee a precise state because we haven't updated the register file yet. If an operand register designator of an instruction being checked for issue matches a register designator in the reorder buffer, then a multiplexer will set to gate the data from the reorder buffer to the register output latch. So this just says we switch back and forth depending on if the most recent value is in the register file or if the most recent value is in the reorder buffer. So it's good. It's a neat thing. So that's what we have here. We basically have some taps into the reorder buffer. And we see that if somebody wants the data, well, we can just provide them the data. And we can not take it from the register file, we'll just take it from this bypass network. Bypassing's very important in computer architecture. There may be bypass paths from some or all of the reorder buffer entries. If multiple bypass paths exist, it is possible for more than one destination entry in the reorder buffer to correspond to a single register. So clearly the latest reorder buffer entry corresponds to the operand designator to generate the bypass path. So this just says if we're changing the state of, say, R4 3 times, well, we only want the last change to R4. We don't want the first change to R4. So when bypass paths are added, preciseness with respect to memory and the program counter does not change from the previous method. So we still have this precise state, and then we're not changing how we handle memory. With memory, we're still doing this thing where we're using these dummy instructions, more or less, that just take up a slot in the reorder buffer, and then we just wait for it to come back from memory. And then we send the actual load or store, of course, to the memory pipeline. The greatest disadvantage with this method is the number of bypass comparators needed, so we're going to need a lot of bypassing comparators. History buffer, okay. Let's talk about a history buffer now. Is it in memory? How is the bypass stored? What do you mean the bypass stored? How is what bypass stored? Bypass is just a connection. Are you talking about the values for bypassing? So the values for bypassing, if we look back here, the result is stored in the reorder buffer. This is the result of the instruction. So we're just bypassing that result to the output of the register file instead of using the register file's contents. If that's what you mean, Brilliant. Or do you mean something else? Yeah, the values for bypass, that's what this section of the reorder buffer is for. This is the result of the instruction. So we basically just have a bunch of taps out. This is just a content addressable this is just a CAM, yeah. Content addressable memory. Okay. Big multi-ported thing, probably. Probably awful for power. Whew, God, I'm tired. Stay up way too late. I need coffee. I was going to get coffee before I came in, but I was already running a little late because I was locked out of my building. I was locked out of my building because it's a Saturday, and I have to sneak in through a different building that has a sky bridge. Okay, the methods presented in this section and next are intended to reduce or eliminate performance losses experienced with a simple reorder buffer. See, this is the problem with working at a public university in a lab, is that it's so hard to get building access. Like, if I worked anywhere else, like being a PhD student or at this like level of research, I would have like a key to the building and I'd be able to get in. But because it's a university, they don't give this access out to any students. Sneaking into my own lab. That's the thing, I'm not even sneaking into my own lab. Once I'm in the building, I have the key to my lab. But, yeah. Okay. So let's see. So, but without all the control logic from multiple bypass paths. So we want to get rid of all these paths because it takes up space and power. And these methods place computer results in a working register file but retain enough state information so a precise state can be restored if an exception occurs. So this just says, well, we'd like to not have to duplicate data and have a ton of paths everywhere, so can we do it better? So that's what this history buffer is. So 5a illustrates the history buffer method. So let's see. So right now, we have a register file, and we still have this result shift register. And we're always getting the values from the register file, and the results are always being written to the register file. However, destination register contents, so if we have something like our, you got to do something. If we do something like an add R4, R2, R3, it says that the destination register contents, so R4 in this case, R4 will go into this history buffer. That way, say what you will, thief. Listen, I'm just an academic. How can I possibly be a thief? I'm stealing knowledge right now. What's amazing? I wish I tried to get into ETH Zurich somewhat, just because ETH Zurich has such ridiculous, they give you such ridiculous stipends. I don't know how it works out after taxes, but like you can make like 75,000 a year as a PhD student there, while I'm making, I don't know, 30 something. Listen, that's why I started streaming. I'll never be able to afford a wedding if I don't pick up a second job, and I'm too much of an out of touch academic to get a regular job. Okay. So basically the idea is we're just saving these destination registers. So Snapchat for subs. Yeah. 70k euro too? Yeah, that too. Or no, it's Swiss francs, right? Switzerland still uses the Swiss franc, right? They're not on the euro, are they? They probably accept both, but don't they still have the Swiss franc? CHF. What does CHF stand for? That's the currency, but CHF. What is it? Congestive heart failure. That's probably not it. CHF Switzerland. CHF Swiss franc. Yeah. Oh, it's like the same unit. It's like the same price of $1. Yeah, it's a Swiss franc. No. No, the Swiss franc is 1.01 USD. I just looked up the conversion. Listen, I need that. That means I'd be making like over double what I'm making now. My cost of living. CHF to euro. Yeah, it's like $1, right? Yeah, it's better than the USD. That's what I was trying to say. Okay, so the basic idea is instead of holding all the results and duplicating all of the results, well, why don't we just store just for the destination registers? So results are written directly to the register file. When an exception comes back, as with the reorder buffer, an exception reports are guided to the proper history buffer entry through the use of tags. When the history buffer contains an element at the head that is known to have finished without exceptions, the history buffer entry is no longer needed and the buffer location can be reused so the head pointer is incremented. Okay. Lightning Mercury. Yo, I just remembered seeing your Reddit post a while back and finally just decided to check it out. Well, hey, Lightning Mercury. It's nice to see you here. I'm Nick. It's nice to meet you. I'm having a wonderful day. It's a great Saturday. It's sunny outside. It's a little hot. It's like 93 degrees. Not as hot as it was when I used to live in South Texas, but, you know, it's not bad. And guess what? I made Italian food earlier. It was really good. Listen, if you're making anything tomato based and it's Italian and you're not using San Marzano tomatoes, you're making a mistake. You've got to rethink that choice. You got to get the red can. What is it? It's Seno or something. San Marzano tomatoes. That's the only tomatoes that you should ever use for Italian. Whether you're making a sauce, whether you're making any dish that's supposed to be Italian. The best Italian I've ever had was at a seafood restaurant. Was it an Italian seafood restaurant? Maybe. Okay, so here's the thing. I actually learned this because I've been recently making my own Italian food. Nope. Oh, hey. Well, nice job on them then. So here's the thing. Do you guys ever notice that every time you go to an Italian restaurant, the sauce might be like different at each Italian place, but you ever notice that do you ever notice that the sauce all has the same kind of undertones and the sauces all taste pretty similar? You guys ever notice that? And I can tell you the reason why. It's because they all use San Marzano tomatoes. I'm in Europe. If it's not literally imported from Italy, it's actually blasphemy. Oh man, that's pretty spooky. No? No what? No to which part? No to the San Marzano tomato part? Because I've been making sauce with San Marzano tomatoes, and it literally tastes like 90% of the Italian restaurants that I've been to. And I'm not talking about the Olive Garden. I don't go to the Olive Garden. No, they taste really different. They can taste really different, but I find that San Marzano, if it's based on a San Marzano tomato, they all have a very similar taste. When something doesn't taste good, you put ketchup on it. Listen, you guys, you haven't seen the light yet. If something doesn't taste good, you've got to expand your palate, and you've got to look to the Middle East for your dipping sauces. So you got to look at that, the Middle East or like Greece. You got to look at that tahini, or tzatziki, or some garlic aioli, or hummus. Listen, changes your mindset on everything. If you thought that fries with ketchup was good, have you ever had fries with tzatziki sauce? Or there's this great place called Mandola's Italian Market in Austin, Texas. You're from the Middle East and don't like hummus? Oh man, that's okay. I went to this place called Mandola's Italian Market in Austin. It's awesome, and they have these garlic fries, and it comes with this pesto aioli. Oh my goodness, those things are so good. I'm pulling them up on stream right now. I wish I lived back in Austin again. Mandola's Italian Market. This place. Oh, it's so good. Let's see. Oh, the gelato there too. It's so good. Oh, here it is. It's like the garlic parmesan fries, and it comes with this pesto aioli. It's so good. The pesto aioli looks kind of weird because it's this kind of like greenish. You don't typically dip in something green, right? I mean, unless it's like spinach or something. So good. Oh, all the cured meats and stuff. Oh, the margarita. Oh, the fried mozzarella. Oh, this is the best. This is my favorite dish there. The tortellini moda mia. This is the peak of Italian right here. This is my favorite Italian dish right here. There's only been one time I've gone to this restaurant and I didn't order the tortellini moda mia. It's a great restaurant though. If you're ever in Austin, Texas, take a look. It's at 4700 West Guadalupe. Or if you're in Austin, you call it Guadalupe. I don't know why, but people like to call it Guadalupe. Let me buy a plane ticket to Austin real quick. Oh my goodness, listen, I'll go with you right now. I love that place. Okay, so the history buffer. Okay, so we talked about the history buffer, and the basic idea is that we're just saving these register file, or we're saving the result, the or the destination register contents to a history buffer. If some exception comes in, we restore the register file state from this history buffer. So here's a history buffer. We'll store the old values in here. And then we have a normal result shift register. And it looks pretty much the same that it did previously, except this time we can still have things like we can now have these integer adds and floating point adds. We don't have to kind of scratch out everything. We can still have these out of order in the result shift register. So now we have the future file. Ooh, spooky. Okay. Oh, I guess I didn't look at example 5. Let's look at example 5 real quick. The entries in the history buffer and result shift register shown in exemplar code. The only difference... Okay, never mind. This is exactly what we already went over. So let's talk about the future file. This is probably a little more interesting. The future file in figure 6... Where's figure 6? Is this it? Nope. Here we go. Future file. So we have a pseudo register file. So we're treating this, what we're calculating all our data on, completely separate now from our real architectural register file. So we'll just keep running around and using this result shift register over and over and over and over. Except if we get an exception, the exception we still have a reorder buffer. That way we can ensure that everything here is correct. But we can run ahead here. But if there's an exception, we can restore from the architectural file. That's a pretty good idea. That is interesting. Now, if anyone can tell me why none of these things really work on GPUs, you get a bonus point. So one register file is the architectural one, represents a sequential machine. And then a second register file is updated as soon as instructions finish, so it runs ahead. So that's this run ahead that we were talking about. Instructions are issued and results are returned to the future file in any order, just as in the original pipeline model. There's also a reorder buffer that receives results in the same time they are written to the future file. When the head pointer finds a complete instruction or valid entry, the result associated with that entry is written to the architectural file. So we're basically only writing things to the architectural file if we know that they're correct. To the register file, we just go, listen, just go. Just give me some performance. If you make a mistake, don't worry, we've got a backup. Oh, you guys are going to have such a fun time. I just realized this. I talk a lot with my hands when I'm speaking, and I must look absolutely crazy in my lab streaming this because I'm very emotive with my hands. So I probably look pretty silly. What was the question? The question was, why don't these methods work on GPUs? So we do things like this on CPUs. We have precise exceptions on CPUs. That very much exists and has existed for a long time. But I will tell you right now for a fact, this is a everyone knows this. This isn't a secret. It's even talked about in the architecture. There are no precise exceptions in GPUs. Now the question is, for a bonus point, why are there no precise exceptions? I'm only a freshman. I don't understand all of this. Feels bad, man. Listen, Lightning Mercury, you're more than welcome to add any questions, ask any questions at any time. And if you ever want to talk about something, or you want to look at something, just let me know, and we can pull it up. This is a free day. This is a Saturday stream. Saturday streams, we have a lot of fun, and all we do is we can look at things, what people want. Because you need parallelism. Can you be any more specific? I mean, we need parallelism in CPUs too. We need instruction level parallelism, we need data level parallelism. We have multi-threading in CPUs now, so we have them both. But it's actually because more than you care about this mechanism. So the reason is uh, there's not a lot of registers on a CPU. There's a lot of registers on a GPU. So a GPU has, each thread has 256 private registers. And you can have tens of thousands of registers at any given moment. So it really comes down to the fact that there's a lot of registers. Now, if we think about where we are right now, if we're having to have 2 copies of this architectural register file, that's really big. We can't just double the register file on a GPU. That would be insane. Let's actually look at let's see if I can find a GPU. Let's see, GPU register file. Images. Let's see if I want the small picture. This one. Okay. So basically, here we go. So this is from Pascal. Pascal uses these. Pascal introduced something a little different than usually. So the register file is pretty darn big. And this is per SM, right? Now and so these are generally called core clusters, right? This is a SM core cluster, or an SM core cluster has 2 SMs, rather. So if we had to double our register file everywhere, it would be not just 2 times this register file, which is 32K. It would be 2 times this in 1 SM, and then we have on Volta, the most recent architecture, we have 80 SMs. That's pretty big just for a register file, and that's not including something like a reorder buffer. So yeah, that's the reason why we don't do that. Does GPU even care about interrupts? Yeah, because we want unified virtual memory. The big problem with GPUs right now is that they're so hard to program because you have to manually manage memory. So if we could just page in stuff, and we could have like virtual memory, like shared memory between the CPU and the GPU. That's like the end goal, right? Instead of having to malloc something, then CUDA malloc something, and then do some mem copy of that entire thing to the GPU, what if we just malloc something and then you just try to execute it? That would be ideal. So in a lot of ways you do care about it. There's also other things that so virtual memory is a big thing that you can better support if you have the ability to handle precise state and precise interrupts. That's the big idea. Okay, so let's see what the idea here is. So example 6, if we consider our code from example 1 again, there's a period of time when the architectural file and the future file contain different entries. With this method, an instruction may finish out of order, so when the integer add finishes, the future file contains new contents for, that's supposed to say R0. Oh, I know what they did. They scanned it and then it was some text-to-text transcription. That's why this is supposed to be a 0, but it got translated to 2 parens. That's what they did. That's why this looks so bad. We figured it's the riddle of the Sphinx. We figured it out. The architectural file, however, does not, and the new contents of R0 are buffered in the reorder buffer entry corresponding to the integer add. Between the time the integer add finishes and the time the floating point add finishes, 2 files are different. Once the floating point finishes, The results are driven into R4 in both files. R0 of the architecture file is written. So as long as we have the correct values and we don't have an exception, then both of them will eventually be the same. The architectural file will eventually catch up, because right now the only difference is if everything goes correctly, the reorder buffer is just kind of slowing down everything from being written to the architectural file. Now, if something goes wrong, then we have to catch up. So in an exception, we restore from the architectural file. Okay. The primary advantage of the future file is realized when the architecture implements interrupts via an exchange where the registers are automatically saved in memory and new ones are restored, as done in CDC and Cray architectures. It's so weird seeing like CDC and Cray architectures everywhere, where instead of seeing something like x86, I'm too used to reading new research papers. There is also no bypass problem, as with the history buffer method. Now, why is there no bypass problem? There's no bypass problem because the future file is automatically just committing everything. We're not storing some values in a reorder buffer that will be needed later. We don't have to pin out from the reorder buffer. In this case, we don't need any of these bypassing because it'll just be in the future file. So we might have, now this isn't to say we get rid of all dependencies, but we get rid of dependencies that were caused by the reorder buffer. We're not going to look at the performance evaluation because it's not really that interesting. Relative performance for the first 14th Lawrence Livermore loops, LLLs. Okay. Reorder with BP? Is that? Oh, bypass, yeah. Okay. And this is relative performance. So, it looks like the number of entries. Yeah, okay. So, extensions. So, what does this enable? So, handling other state values. So, most architectures have more state than we have assumed. For example, process may have state registers that point to page and segment tables, indicate interrupt mask conditions. The additional information can be used with a similar method as to that used for stores to memory. Okay. So basically what they're saying is that if we need to make the table bigger, make the table bigger. We can store as much stuff as we want. We have transistors to spare. See, this is how architecture worked up until very recently. Up until very recently, we said we have billions of transistors. Do whatever you want with them. Or maybe back in the day, we had millions or hundreds of thousands of transistors. We have more than we know what to do with. Build out a table. Build out another table. And that's why you'll see that all of these things are based upon, we made tables everywhere. Virtual memory. So virtual memory is a very important reason for supporting precise interrupts. It must first be possible to recover from page faults. First, the address translation pipeline should be designed so that load store instructions pass through it in order. This has been assumed throughout the paper. Depending on the method being used, the load store instructions reserve time slots in the result pipeline and or reorder buffer, and are read no earlier than at the time at which the instructions have been checked for exception conditions, especially page faults. For stores, these entries are not used for data, just for the exception reporting. Now, the reason for that is it's a store. We're not using the data. We're just storing data. If there's an addressing fault, then the instruction is canceled in the addressing pipeline, and all subsequent load store instructions are canceled as they pass through the addressing pipeline. This guarantees that no additional load stores modify the process state, not suite. The mechanisms described in the earlier section for assuring preciseness with respect to registers guarantee non-load store instructions following the faulting load store will not modify the process state. So it's precise. So basically we can just leverage and extend out what we already have to support, say things like virtual memory. Cache memory, and they talk about store through caches, or write through, or write back rather. Or there's write back and there's write through. Yeah. This is probably store through is probably the same thing as write through. Thus, as far as we assume systems do not use cache memory, well, that's a bad assumption. We like to use cache. Caches are good. Inclusion of the cache in memory hierarchy affects the implementation of precise interrupts. As we have seen, an important part of all the methods is that stores are held until all previous instructions are known to be exception-free. With the cache, stores may be made into the cache earlier, and for performance reasons, should. The actual updating of main memory, however, is still subject to the constraints as before. So let's talk about store through caches. So that's where the cache can be updated immediately, while store through to main memory. So we update the cache, but at the same time, we're also updating the other level of the memory hierarchy. Okay, so load instructions are free to use cache copy. However, regardless of whether the store through has taken place, this means that main memory is always in a precise state. But the cache contents may run ahead of the precise state. If an interrupt should occur while the cache is potentially in such a state, then the cache should be flushed. So this just says that because of the method we're using with store through, where we make sure that all the stores get sent all the way to main memory, we may run ahead with the loads, but if we eventually hit a problem, well, okay, we can recover as normally, and then we just flush the cache and say, okay, all of you are an invalid now. None of you represent true values because you're from that weird exception run-ahead state. So the alternative is to treat the cache in a way similar to the register files. One could, for example, keep a history buffer. This does not necessarily mean a performance penalty because a cache must be checked for a hit prior to the write cycle. In many high-performance cache organizations, the read cycle for history data can be done in parallel, both the hit check. So the hit check and the read cycle can be done in parallel. The buffer entries can be used to restore the state of the cache. So basically, they're saying that you could use that future file again. Now, for a write-back cache. A write-back cache is perhaps the cache type most compatible with implementing precise interrupts. This is because stores in a write-back cache are not made directly to memory, so it just stays in the cache. There is a built-in delay between updating the cache and updating main memory. Before an actual write-back operation can be performed, the reorder buffer should be emptied, or should be checked for data belonging to the line being written. If the data should be found, the write-back must wait until the data has made its way to the cache. If a history buffer is used, either a cache line must be saved to the history buffer, or the write-back must wait until the associated instruction has made its way to the end of the buffer. So in this case, write-back will sometimes have to wait until a precise state is reached, which is good. Linear pipeline. That's boring, linear pipeline. So here's an example of a linear pipeline structure. We had this bypass network. Okay, so what are our summaries and conclusions? Oh, I love this section. Look how short it is. They did such a good job. 5 methods have been described to solve the precise interrupt problem. These methods were then evaluated through simulations of the Cray 1S. Degradation can range between 2.5 and 3%. It is expected that the cost of implementing these methods could vary substantially, with the method producing the smallest performance degradation probably being the most expensive, because we're building all these tables, and the tables are going to grow the more we want to flesh them out. So it's important to note that some indirect causes for performance degradation were not considered. So longer control paths, lengthening the clock period. So if we're adding some extra hardware in the way, we're going to make our critical path a little longer. And then the additional control logic, greater board area, which means more wiring delays, also lengthening the clock period. So we might make the clock period a little bit longer, so that 3% might creep to 5%, something like that. But yeah, that's the basics of precise interrupts. This is what began precise interrupts. So Jim Smith wants to say thank R.G. Hintz. Oops. I don't know what that was. Okay. Well, let's give a big round of applause then to R.G. Hintz and J.B. Peterson. Wait. Oh, Pearson, not Peterson. Of Control Data Corp, a corporation, for whom he was associated during the development of cyber. This paper is based upon research from the National Science Foundation. Isn't that cool? We just learned about precise interrupts. And then yesterday we talked about how would we do this for interrupts on the on GPUs. So there's been about 2 papers that have looked into that we've gone over already. Those are pretty cool. Okay. How's everyone doing still? Everyone still having a wonderful day? I think we had a good time going through this research paper. Anyone want to look at anything real quick before we end the stream for today? Anything at all? Anything at all research related or engineering related, computer engineering related? I'm more than happy to pull it up on stream and we can talk about it a little bit. Is anything confusing you? Is there anything you want to do in your personal life to make you a better engineer for tomorrow? You want to read more books? Nice. What kind of books do you want to read? Time, though. Oh, listen. I know what you mean. Life gets in the way, doesn't it? You want to read more fiction books? More non-fiction books? Reference books? Learning books? What do you want to read? I haven't read a lot of fiction recently, but I really enjoyed pretty much every Steinbeck book. I used to read them all the time. Fiction. A lot of people don't like fiction. Non-technical books. Yeah. I don't know why there's such a bias against like non-technical books. It's like, oh, if it's not technical, don't. It's awful. It's like, sometimes. I don't read a lot of non-technical stuff. I mainly read technical stuff, and that's both because I find it interesting, but also out of necessity. But honestly, right now, I just want some coffee, guys. Guys, I just need some coffee. Listen. What are the best coffee beverages? So, coffee, 1. Coffee's a great beverage. Not in any particular order. Coffee, really good. Use Audible. Audible's pretty good. I tend to zone out when I'm ever listening to books. I like what I do here, where I'll pull a book up and I will just like write all over the book, and I'll just write notes everywhere, and then I'll work out things on the side. So Audible doesn't work well for me. I think I listened to 2 books on Audible. One of them was The Emperor of All Maladies, which was like a history of cancer, and then the other one was I don't know what the other one was. Someone like gifted me like The Art of War by like Sun Tzu, and I listened to that. I don't think I finished it because I was bored, but I found The Emperor of All Maladies, the history of cancer one, to be more entertaining than The Art of War. I don't know if that says anything. The problem I have with a lot of books, like that is that a lot of the stuff is just kind of intuitive, right? Listen, let's pull up the Art of War and let's look at the key concepts from the Art of War. Key concepts, Art of War. Best lessons and summary of the Art of War. Where's my bullet? Listen, here we go. Recklessness, which leads to destruction. Cowardice, which leads to capture. A hasty temper, which can be provoked by insults. A delicacy of honor, which is sensitive to shame. Listen, all of these things are all of these things are intuitive, right? Like if you've these are all things that these aren't necessary. They're very simple concepts, right? But I think most learning things are simple concepts. It's just a matter of actually following through them. The Art of Learning is a cool book. What's the Art of Learning? The Art of Learning. This is by Josh Waitzkin. Where is... I just want the wiki, right? That's just a summary. Okay. The Art of Learning explains the science of becoming top performer based on Josh Watkins' personal rise to the top of chess and Tai Chi world by showing you the right mindset, proper ways to practice, and how to use the habits of a professional. Okay. Seems like a pretty interesting book. Let's look up this guy. It's more like a story rather than the self-help stuff. I hate the self-help stuff because all the self-help stuff is the same, and anybody that reads a self-help book already knows everything that's in the self-help book. It's like, get out there and do something, and then it's like, wow, that's a great idea, and then they put the book down and then they flip on the TV or something, right? Like, self-help books are pointless because they just reinforce stuff you already know. The jump comes to actually doing it. Okay, so let's look at this guy. Oh, okay, so this is Bobby Fischer. Okay. Oh, that's interesting. Yeah, if you ever want a good book to read, I would suggest this one. It's called The Innovator's Dilemma. It's from the Harvard Business School guy that this book is really good. The guy that wrote this is a Harvard. He's a big guy in the Harvard Business School. What's the guy's name? I forgot what his name is. Oh, Clayton Christensen. That's what his name is. And it's all about, like, I think it's all about like hard drives and stuff. I've been meaning to read this book, but I've heard great things. Also follow Evan the Bouncy for more AI PhD stuff. Neat. I'll take a look at him. Evan the Bouncy. Click. Click. Evan the Bouncy also has a GitHub. Let's see Evan the Bouncy's GitHub. Matching parentheses RNN. I was just looking at an RNN thing, but it was some work from AMD. That's what I was looking at. Neural network stuff. On Twitch, yeah, I assumed he's on Twitch. I just Googled it and I found the GitHub. I'm assuming this is the same person. And I'm guessing on Twitch he does his Dota stuff, right? if he has a repo for this. Oh, he's really happy with this one commit. Yeah, I'll take a look at him. AI stuff is pretty neat. I really only care about the architecture side of AI and machine learning because it sounds like really pompous to say this, but of course AI needs the foundations, right? You need the theoretical computer science foundations of AI. But there's a reason why AI existed in the 50s and then nothing happened. Then AI existed in the 80s and nothing happened. And AI existed in the mid 2000s and then it finally kicked off. There's a reason for that. And that's because the hardware finally got good enough that we could do AI. So my interests in AI are mainly related to my field, which is how do we accelerate machine learning. Which there's some things that are interesting in it, but honestly though, my interest in AI is very limited because AI I actually found to be really boring. So what do people do to accelerate AI? Well, they, at least for inference tasks and stuff, they do reduced precision. So use int8s or use like Microsoft for their brainwave thing has some like proprietary 8-bit floating point format that they use. That's from their brainwave stuff where they have it's all on FPGAs. They're Stratix 10s. Then the other way is like finding ways to do pruning and exploit like sparsity. There's no more software boundary to push. Really? I mean, I haven't looked into the theoretical side really at all, but I'd imagine that that's probably pretty close considering that the field's been around since 1950-ish. I can't imagine that. I'd imagine that we're getting to the point where add more layers. But we've already found how many layers is good, right? Like with RNN for LSTMs, it's what's the common thing? Isn't it like 128 layers or something? It's like people don't use more than that. And like same thing with all the named ones. It's just a set amount of layers. I don't think you get infinitely. You don't get. It's like pipelining. I don't think you get really more and more benefit though adding layers. Unfortunately, it'd be nice if you did. All right. I think we've had a wonderful day today. I want to thank you all for stopping by. I had a wonderful time seeing you all today. If you want to follow me so that you can see when I go live or whenever I'm doing research related things, feel free to give me that follow on Twitch. Follow me on YouTube. I post every video that I make on YouTube. If you ever want to buy me coffee, you can donate. But like I said, never feel obligated to donate to me. I have fun streaming for you guys. Not to mention, I use this for my research, so it's self-serving. I need to do this anyway, at least the research part of it. But now I get to share this research with other people. But like I said, I'm Nick from Engineering Today. And I hope you learned something today. Robbie, thanks for the stream. No, thank you for being here. I appreciate you joining us today. Alright everyone, have a wonderful Saturday. Or if you're in the EU time zone and it's Sunday already, have a wonderful Sunday. I'll see you guys later.